Okay, good afternoon, everyone. Yep, so, let me tell you, so just a quick announcement that I'm gonna post like solutions to the assignment, and I should be able to mark your assignments pretty soon. Okay. And then also I'm posting a new assignment today that will be due next week, Friday. That would be assignment 3. Okay. Okay. When is coursework 1? I can tell you. Just a moment. So the coursework 1 is going to be on Wednesday, March 10th. Okay. Topics are going to be just things from assignment 1, 2, and 3. Let's see. Like, and related, whatever is related to those topics, those assignments. Let's see. The time of the exam, I have to get back to you on that. But that is just some general information. Okay. So I guess let me just say more details soon. Okay. Okay. So for today, basically we're going to start talking about group actions. Okay. This topic is actually kind of like the original motivation for, constructing groups and defining what they are was to study group actions, So actually before we had groups, there was still group actions before that, and then someone decided, I forget who, someone decided like maybe it's good to study groups too. Okay. Before I define what they are, let me tell you a few examples. Okay, so G is going to be maybe like S4. This is sigma such that Sigma is a permutation. On 1, 2, 3, 4. And then, so whenever we talk about group actions, we have a group and we have a set, and the group does stuff to the set. So here's my set is going to be 1, 2, 3, 4. Okay. And I have to explain how does S4 act on X. So for a permutation sigma and X in the set, define sigma times X to just be, well, it is kind of like one thing that it could be. Sigma is a function from 1, 2, 3, 4 to 1, 2, 3, 4. So we should just define sigma times X to just be sigma of X. Okay. So this one, it's kind of seems pointless. But the reason is like the group S4 is defined by its action on 1, 2, 3, the set 1, 2, 3, 4. So you get a very natural group action. Okay. And I want to just do the actual definition of group action after we do just a couple examples. Okay, another example. You can do G might be the integers. And then X is also going to be the integers. This is the integers under addition. Okay. And the group action might be like, you know, might be just translation. So G acts on X by just doing G plus X. Maybe I'll give this like a star or something. Okay. Okay. What's another thing that we can do? What other types of groups we have? We have like groups of matrices, right? Oh, sorry. So we have G could be like GL2. Let's GL2R. In other words, the set of 2 by 2 invertible matrices.
Say.
Okay, did someone have a question?
Yes, at the density last part of 2.
Oh, sorry. Okay, let me just switch back. Oh, sorry about that. So we just do like G star X is just G plus X.
Okay, thanks.
Okay. And I'm just writing down some different ways that a group can you know, do something to like some set. Okay, and here my group is going to be matrices, 2 by 2 matrices. Well, matrices are like linear transformations from R2 to R2. So I can say that X might be the vector space R2. And if I have a 2x2 matrix G and a vector X, Y in R2, so G might be like A, B, C, D. Then, I can do, I can combine G and V and get another vector. And I can do that by just regular matrix multiplication. Okay. And there are actually many, many more examples. But that is enough for now, and then we'll see more later. Okay, so the key properties we want to take away from these examples is like somehow when you let a group act on a set, basically we want to have like some kind of associative property, and we want the identity element to just kind of be the identity, give you the identity function. Okay, for example, we can look at the identity times the identity matrix times XY. The identity matrix is just 1, 0, 0, 1. And when we plug it into the like regular matrix multiplication, we see it's like X, 1 times X plus 0 times Y. 0 times X plus 1 times Y. You get XY back. Okay, so the identity matrix, when it acts on R2, it acts as the identity as well, okay? So you want that to happen. Okay. So now I want to write down our definition. Okay, so we have a group and a set X. A group action is just a function alpha, and the input to alpha is a group element and an element of the set, and then the function alpha combines it into a new element of the set. And there's like some properties it satisfies. So the first property is that alpha G we want some property like that. Okay. The second property is that we want, oh yeah, and this should hold for all G and H and X. Okay. Okay, and then sometimes, so you see like I have this alpha here and I didn't have any alphas in my examples. Okay, and then, so I just want to make the note. Sometimes you just abbreviate, we just like leave out the alpha. G times X for alpha GX. Okay. And then if I rewrite these two properties with this abbreviation, so one just means that G times H times X is just GH times X. Okay, and let's like try and parse what this means. Your H times X, that's H acting on the set, the element of the set X. So H times X, that's another element of X. And then G is acting on that. Okay, so H times X is an element of X, and then G acts on that somehow. And on the right-hand side, we have regular group multiplication of G and H. And then you multiply those in a group, and then you apply the result to X. And 2, it can be written, it just says that when you let the identity element of G act on X, you get X. Okay, so so if it's clear, like for certain examples, I might like omit this alpha, but I might put in the alpha when we prove things about group actions. Okay, and also let me make another note. We should really call this what we have defined as group action is really a left group action. Meaning that when G acts on X, it's like GX. Okay, there's other group actions where, you know, instead of when G acts on X, it's like XG, and that would be like a right group action. I don't want to talk too much about that, but just know that, you know, if you might see, you know, in the world, you might see right group actions. Well, that's something slightly different. Okay. Okay. Okay, so the first thing we want to see is that there's kind of like when a group acts on a set, each element of the group can be viewed as a permutation. Okay, so we want to try and explain that relationship. Okay, let me first do like 2 examples. Right? So let me put in the alpha just so we see. So we have alpha So here's an example. G is Z and X is Z. So when I'm okay, and then alpha from G times Z, or is G times X to X is alpha N X is just N plus X. And then the two properties of being a group action that we have to verify. We have to verify that if I do N plus M, that is the same thing as alpha N alpha M X in order to have a group action. Okay, so let's just verify, like, oh yeah, and we also have to verify that alpha 0 X equals X. Okay, let's verify these two properties. Then we'll know that this is really a group action according to my definition. Then we want to see how elements of G give like permutations. Okay. Okay, so we just look at both sides of this, like it's supposed to be an equality. So on the left-hand side, you have alpha N plus M applied to X. Well, alpha just says take this integer and add it to this integer. Okay, on the right-hand side, we have alpha N, alpha M, X. Alpha MX is just M plus X. Then alpha says take this plus this, so that's just N plus M plus X. Okay, so both sides, I mean, really this is saying like the associative law, but which is fine. Okay, so by the associative law, these two things are the same. Okay, so we really have a group. So if we have the first property satisfied, if we do this, we see like alpha 0 X is just 0 plus X, which is just X as well. Okay, so that verifies both the properties of having a group action. So we have a group action. Okay, so alpha gives an action, a group action of Z on Z. And the action is by like translation. Okay. So now we look at maybe the element G equals 1 in Z, as we're thinking of 1 as an element of the group. Okay. And we look at what it does. Look at what happens to each X and Z when G acts on it. Okay. So G times 1, that's just G plus 1, that's just 1 plus 1, that's 2. So if we like record it, G sends 1 to 2. What's G times 0? Well, that's just G plus 0, that's just 1 plus 0, that's 1. G sends 0 to 1. G times minus 1, that's just 1 plus negative 1, that's just 0. So G sends negative 1 and maps it to 0. What about 2? Well, that's just G plus 2. Again, you could, you have 1 plus 2. Okay, so G sends 2 to 3. Okay, so G takes an integer and shifts it over 1. So G kind of corresponds with this permutation on the integers, the kind of shift shifting function, I guess. So you have -3 goes to -2, -2 goes to -1, -1 goes to 0, 0 goes to 1, and goes to 2, and on like that. Okay, so we can think of this group action identifies the group element 1 with this permutation on the integers, this shifting permutation, I guess. Okay. So a group action gives us a way to view our group elements as permutations. Okay. So that's our plan. Of course, like some groups are already permutations. And in that case, like this kind of matches up with the way the thing was defined, but not all of our groups are naturally permutation, you know? Okay. Okay, so first, let's just see that we get a homomorphism. Okay, so let's write down this proposition. So they define capital Phi from G to the symmetric group on X, where alpha is the group action of G on X, and we define this phi by phi of G is a certain permutation on the elements of X. Okay, so phi of G is a permutation. I'll try and denote it like this. Is a permutation that X gets mapped to alpha GX. Okay, so for a particular G, G can be like act on this element X by alpha by doing this. Okay, now again for this particular G, it'll like switch around all the elements of X somehow, and so we get a permutation. Okay. So then phi is well defined and is a homomorphism. Okay. So to show that phi is well defined, there are several things we have to do. We have to show that this thing is actually a permutation of X. Right, and then that will tell us that this function is well defined. Okay. So let's prove this. Okay. The G and G. We must show that phi of G from X to X defined by X. So this is a capital X. I guess I should put like little ticks on it. But the definition of phi of g is that x gets mapped to alpha gx. Now we must show that this is a permutation on x, and then after that we have to show that phi of gh is phi of g times phi of h. That's what we have to do after. Okay. So let's try and we just have to show that this is a permutation, right? So we have to show that this function is one-to-one and onto. Okay, so let's show it's one-to-one. I think there's a quicker way to do this, but we'll just do it the boring way, I guess. So let's suppose that alpha gx equals alpha gx prime. We have to show that x equals x prime. Well, just do let G inverse act on both sides. So if you do alpha G, if you let G inverse act on the left-hand side, what happens? Well, the associative law tells us this is just alpha G inverse G acting on X. G inverse G is just the identity. And E times X is just X. So on the left-hand side, you get X. If you let G inverse act on the right-hand side, you just get X prime. Okay. So we started out with this equals this. So since this equals this, and we just did the same thing to both sides, so both sides have to be equal, so x equals x prime. Okay, so this function is one-to-one, and we just have to show it's onto. So now let y be an x. Then notice that we can write y as what? Alpha g inverse y.
So can you carry it up some more, please?
Oh yeah, sorry. There we go. Okay. So in other words, if I want this to map to y, I just choose x to be alpha g inverse y. Like g inverse act on y, and then when g acts again, it just the g inverse goes away. Okay. So that tells us that phi of g is one-to-one and onto. So that means that phi of g is just a permutation of the elements of x. That's what we wanted. Okay. So for every group element, we get a permutation. Now we just need to show this this formula. Actually, if we had done this first, that makes this part easier, but that's okay. So we now show this formula. So now we need to show, so now we have, right now we have a function phi, which takes an element of G and gives us a permutation on X. And of course, the permutations on X is a group, G is a group, and so we want to have a homomorphism. Okay, so we need to check. So let G and H be in G, and we ask ourselves, how do we show that phi of GH equals phi of G times phi of H? Well, how do we do that? Well, these are both permutations on X. So we have to check, is phi of GH of X equal to phi of G phi of H of X? So we choose an arbitrary element of X and we apply phi GH to both sides. So the left-hand side first, phi GH of X, well, the definition of phi GH just said that this is just alpha GH of X. What's the right-hand side? Well, phi G times phi H. If I apply that to X, well, here, this is the product of two permutations, and we multiply permutations by composing, right? So this means that first we do phi of H, apply that to X, and then we do phi of G of that. Okay, phi of H of X is just alpha HX. Phi of G of that is just alpha G of alpha HX. Okay. Now we see that this is just like one of the properties of being a group action, that alpha GHX